Have you ever wondered what the Earth would say if it could speak? Sometimes it doesn't need words, it speaks through movement. In 2016 and 2017, central Italy's Apennines shook with powerful earthquakes. The land shifted, the mountains trembled, and the ground rose and fell, leaving a mark not just on the landscape, but in the lives of thousands. But can we truly understand the language of the Earth? With a study entitled Ground Displacements Estimation through GNSS and Geometric Leveling, a Geological Interpretation of 2016-2017 Seismic Sequence in Central Italy, scientists didn't just listen. They translated those whispers into data, maps, and stories, unraveling the mystery beneath the surface, which set out to answer a big question on how the ground moved during these earthquakes and why. In this video, I will tackle the objectives of the study, the methods used in gathering the data, results and/or the findings of the study, and lastly, the conclusion. The study has two key objectives. First is to measure the ground displacement caused by the seismic events. Second is to interpret these shifts in the context of Central Italy's complex geology. The map before you represents the study area of this research, in which it highlights the main fault system driving seismic activity. The Mount Vittoria, Mount Bob Fault System, or VBFS, and Mount Flaga Fault System, or LMFS, are central to seismic activity in the region. These faults form part of an extensional tectonic regime where the Earth's crust is pulling apart. The pink shaded areas mark where significant seismic surface ruptures occur during the earthquakes, or in simple terms, it is where the ground broke open during the earthquakes. This map also includes the epicenter of the past earthquakes, connecting the 2016 to 2017 sequence to the region's long tectonic history. This map frames the study, illustrating how the seismic sequence fits into the larger picture of Central Italy's geological evolution. The study also provides a cross-section of the mountain, in which it reveals the intricate fault system underlying the Apennines. Notice the Mount Vittoria, Mount Bob Fault System, and the Laga Fault System extends into the deeper layer of rock. These faults are linked to the Olivano Antrodoco Sibillini Thrust, or OAS, a regional tectonic feature that influences how seismic energy propagates. This map shows how shallow faults connect to the deeper structures, helping us understand the dual forces shaping the region's seismicity. As we all know, understanding the Earth requires precision, patience, and creativity. In this study, researchers used two main techniques: Global Navigation Satellite Systems, or GNSS, and geometric leveling, which work together like translators. GNSS is a satellite-based system that tracks horizontal and vertical movements with millimeter precision. In this figure, it shows a distribution of GNSS stations that each represented by the triangles. These stations form the backbone of horizontal and vertical displacement measurements, and by analyzing the pre- and post-earthquake data, researchers pinpointed how the Earth's crust moved during the seismic events. The second method is geometric leveling. This method uses ground-based measurements to track vertical displacements along the 350 kilometers of leveling lines as shown in this figure. Each dot represents a remeasured benchmark, forming a network across the affected region. These techniques created a detailed 3D map of the ground movement, laying the groundwork for the study's findings. The study's findings shows in these figures. This map illustrates black vectors, which shows horizontal displacements at GNSS stations. Each arrow's length and direction represent the magnitude and orientation of the ground movement. The data aligns with known fault systems, confirming that no more faulting drove the seismicity. The next three figures shows the data gathered from the geometric leveling method, which revealed dramatic vertical shifts. In line 124, near Pescara del Toronto, the ground dropped by 40 cm. This drop corresponds to the area near major fault ruptures. And in line 125, at Fort Canopine, subsidence peaked at 60 cm, highlighting intense seismic deformation. And while in line 9, in contrast to the previous lines, the movements here were subtle, reflecting areas that were less affected by the earthquakes. Furthermore, the results from this research also confirms the influence of large tectonic barriers like Olivano and Trodocco Sibylinitras that may have influenced the propagation of the seismicity of the area. In conclusion, the study's results provide a clear evidence of how the 2016 to 2017 seismic events were driven by normal faulting. However, the data also pointed to the influence of deeper tectonic features such as the Olivano and Trodocco Sibylinitras, which played a role in shaping the region's seismic response. The integration of GNSS and leveling data gave us a complete picture of the ground movements, both horizontal and vertical, highlighting the interconnected nature of surface and subsurface processes. These findings not only advance our understanding of seismic behavior in central Italy, but also offered critical tools for improving disaster preparedness and response worldwide. The earthquakes of the 2016 to 2017 reminds us that the Earth is constantly changing, but with studies like this, we're learning to listen, to understand, and to act. By combining advanced technology and detailed fieldwork, we've turned the Earth's movements into knowledge that can save lives and build safer communities.